Hello. We shall see here how AC is converted to DC by a item called bridge rectifier, or using 4 diodes in the bridge configuration being fed from the supply. In the supply we connect to the bridge configuration anode cathode points one side, the other side of anode cathode is given to the bridge rectifier, and the cathode is connected to ultimately a filter capacitor. Here we have tried to keep a simple small resistor in series in order to see how the capacitor is getting charged, and we also have connected a voltmeter, a DC voltmeter across this to see how the voltage is building up in the capacitor, which can subsequently be used. This is operating in a very low frequency, and the things that you see here is actually happening very fast once you go for a higher frequency, but this is for the understanding purpose. We are given the low frequency operation for you to see it better. Now if I simulate this, you see this capacitor is now starting charged, voltage is building up, and current is, you see, in only one direction. AC is in both directions, this way and this way, whereas DC is in only one direction, and the voltage slowly goes up, building, and after the voltage builds up to a level, the charging of the capacitor will stop if no load is connected. We will first see how the charging of the capacitor is taking place, and after the input voltage which is supplied at the AC end reaches to a level that the capacitor is going to be fully charged, and these are normally electrolytic capacitors. And once the electrolytic capacitor, they are polarized capacitors, and we have to have this side is positive, this side is negative. We have to have positive supply to this side and negative to this side. Connecting it in a reverse way would create havocs. It will burst, and it's not advisable at any time to connect it in a reverse position. Now what we see, the voltage is going on increasing. It's still the DC voltage is flowing because there is no load connected. This capacitor will go on building the voltage to a level after which the charging will stop, and only if we go over to connecting it to a load. For example, we have a load here. I have not connected the load here yet, so it is going on charging, and if I now maybe close this resistor, it will charge to the fullest much faster. See, now the voltage is charged to about 10.6, 10.7, and finally it will go to a voltage which is sent by the input AC. The input AC is roughly, we can connect a ammeter at the input AC, or we can see what is the input AC, and this voltage is going on. Finally it has reached at a level of about 10.7 volts. And in this process, if we start drawing the power, supposing this is a practical situation where there is no resistor here, the filtered, the pulsating DC is given to the capacitor, and then the capacitor ultimately is getting fully charged. And at this juncture, if I switch on the load, see what is happening. The voltage is falling and charging is falling, and the charging is taking place, and then the falling is taking place because of the the power being drawn from the capacitor. So this is what actually happens. And if supposing the load is of very high resistance, that means the current is very low. For example, if I change, now if I stop this, and if I change the value of this load to a little higher value, now supposing this was only a 10.5 ohms resistor, now I make it a, say, a 10K register. Okay, and the same situation I would like to see what is happening. See, discharging takes place. The voltage is roughly maintained at 10.6 volts and the current drawn is 1.5 milliamperes. This we would like to see, and we can see how the load is behaving, and we can see the operation in the CRO. If we go for a CRO, if I connect the CRO here, we go to this and give it a CRO connection. CRO is at A we have given, and then if we connect this and we go on switching on this, and we find that there is an absolute DC that we get here. When we simulate this, we get the absolute pure DC. We get a pure DC here as far as the output is concerned. Because the load is here very low in the process, the capacitor is able to supply whatever requirement for the load. So you get a steady DC. Of course, the change in the AC input here will change the DC output here. This we'll see in the subsequent slides and the subsequent operations for understanding it in a better way.
Hi, today we shall discuss about DC power supply. Every electronic circuit requires a DC to operate. So also our project. So for our project, we have incorporated our own DC power supply. Our own DC power supply. So let me start with how we get it. This is a transformer, step-down transformer with 230 volt AC input and 12 volt AC output. And we supply 230 volt AC from the source, supply source. We get 12 volt AC here. Rest all components are in fact mounted on a printed circuit board, so that is why we have a connector here. And the 12 volt AC, which is coming out from the secondary of the transformer, through a connector arrangement goes to the board. And from there, these connections are going to a bridge rectifier comprising of 4 diodes, and they are IN4007. That comprises a bridge rectifier. And we know a bridge rectifier ultimately gives a pulsating DC at this place, which needs to be filtered, and that is filtered by this capacitor. And we call it unregulated 12 volt because while this voltage, input voltage, varies from 230 volt to say a lower voltage, say 200 volt, this also will vary in that proportion because we know that V1 by V2 is equal to N1 by N2. So when this also varies, the input to the bridge rectifier also varies, so the output from the unregulated output from the bridge rectifier also varies, and we call it unregulated because this may vary depending on this voltage varying. If this is low, this will be less than 12. If this is high, this will be higher than 12. But since all our circuits require a fixed voltage, we use after the filtration, what we use a voltage regulator. We call it a 7805 voltage regulator. The 5 means it's a 5 volt regulator. Sometimes we use 7806, 7812, 7808. Accordingly, the voltages are fixed for that. So here we get regulated 5 volt, meaning if this voltage at the input changes from 9, 10, 11, 12, 13, 14, whatever may be, this voltage remains constant at 5 volt. So when this remains at constant at 5 volt, to know that this voltage is available at this particular point, because that will be the feeding point to all the circuits that we will subsequently assemble or subsequently use, then we connect a LED in series with a resistor. Every LED is a diode, so this resistance is a must to be used in series with this. Anode goes to positive and cathode goes to negative. We call this is as positive and this is as negative. In all electronic circuit, it is normally said as ground, but there is nothing like ground. This never flows, this positive never flows to ground. Ground is a word which is followed in the electronic circuit. Actually, the current flows, suppose this LED has to glow, the current will flow from here, 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 and here, or here. Ground meaning that anywhere I provide a ground, it is a negative path, and this is the positive path. This is how a DC power supply works for any kind of microcontroller applications where we need 5 volts. There are also requirements in a circuit, unregulated voltage. So if at all we require a 12 volt for driving some other equipment like some other components like a relay or a motor, we will take the supply from this place. Because a relay with an unregulated voltage of 12 volt will not have much difficulty in operation. Even if this falls to 10 volts or goes to about 14 volts, the relay is not going to be affected. Or a motor, if we use, it is not going to be very severely affected. That is why we provide unregulated voltage from here, but the regulated voltage is going to all the electronic circuits like microcontrollers and digital circuits, transistors, operational amplifiers that we shall be using for our projects. So that makes the DC power supply requirement for the project complete. Thank you.